There, now we got the stream going too. Yes, so for those of you who are not part of this generation's children, it's stuffy is the accepted term for stuffed animal. It just is. That's just a universal thing they've all decided on. So, alrighty. So now you should be able to see the web page, yes? Okay. Much less interesting, but we got to do some business eventually. I have not gotten around to finishing recording the end of lecture one yet. I had a task yesterday that had to get done, and so I spent yesterday and earlier today doing that. I hope to be able to do so tomorrow, but none of that material is necessarily linked to what we're going to continue talking about, so we don't need to worry about that too much. One thing I did do a couple days ago and I forgot to mention is add another article to your reading list that goes with this unit. So Cohen 1994 is a paper that is available for download in Icon under the files. It is a classic paper. It has a very funny line in it that I wanted to share with you guys. So this is a paper that is critiquing null hypothesis significance testing, and it's titled "The Earth is Round, p less than 0.05." So it's very funny, and he describes his arguments and agreements with contemporaries. And there's a quote in here that I love where he talks about the acronym Null Hypothesis Significance Testing, NHST. I resisted the temptation to call it Statistical Hypothesis Inference Testing. Wait for it. Think of the acronym. See, it would stand for shit. See, that's funny. Stat humor. Yes, so I've never had the chance to meet him, but I wish I would have. He seemed like he would be a fun guy to have a beer with or something like that. So Jacob Cohen as one of the greats in the field. So I wanted to make sure that that got added to our list because still today there is a big push against null hypothesis significance testing. So that will guide some of my recommendations as to what information you would want to make sure to give your readers in describing analyses so that they are not going to have the same problems that are described in this article. So that is available on Icon for you. Homework is going on right now. So let me find where we are here, week 4. As I mentioned last time, I pushed the due date back for homework 1 3 days. So it's not due until a week from today. Does anyone have questions on homework 1? So I'll let you think about that while I catch up on the chat window. Is this the same Cohen as Cohen's kappa? Quite possibly. Cohen did a lot of things. He's well known for power analysis in particular. Um, his wife actually was in the field, so if you're familiar with, there's a linear regression textbook that's Cohen and Cohen. It's Jacob and Patricia Cohen. They were the authors of that. They have a very nice dedication to their other successful collaboration, Gideon, I believe, is the dedication, their son. So, teaching English, talking about pronouns. He, she, it. Yes, another unfortunate abbreviation if you were to put that together. So, yes, beware of pronounceable acronyms, I think is the general rule we can follow. Question another one. Does anyone with a Mac successfully downloaded everything? I have everything, but Stata won't load. So I can help you troubleshoot that if you want, if you're able to come to office hours, or else we can set up a time to meet. Otherwise, if anyone wants to try to help with that, um, the same techniques in terms of getting Stata to recognize where your files are, relying on Windows Explorer inside the virtual desktop will be your best bet. That's the one piece of advice I can tell you off the top of my head. Otherwise, if you could set up a meeting with me from a computer where you can share your screen so that I can see whatever error messages are being generated and help walk through the troubleshooting of those. So let me know if you need that. Yes, send an email, please, and we'll set up a time. Any homework 1 questions? I have that pulled up in case anyone wants to ask. Okay, you should be able to do all of it. If you run into any problems, let me know. I did have one question about population values for the test of means. Those are given in the questions. So if memory serves, make sure that I said this correctly. In section 2, you're being asked to test sample means against population means. And it is an age of 28 as the population mean under section 2, and it is an undergraduate GPA of 3.6 as the second set of questions. And so those are the values that you would tell the software to use in testing your obtained sample mean against those values. Just so you know the structure of your homeworks, what's actually going on under the hood is that each of you has your own data set. I use the same specifications and the same story, but I use your ID numbers as the random seed by which to generate the data. So all of you are going to have slightly different answers. So if you work together on this, just know that whatever process that you've found that works, you'll each have to run on your own data set to be able to get the right answers. And also, any of the questions down here that refer to your results, for instance, question 60, which of the following is true about mean years of age? It's referring to the results that you got specifically. So which answer is correct is conditional on your own findings. So just keep that in mind if you're talking amongst yourselves. That's the way that it's set up. Okay, so any homework questions? Okay, let me know via email if you do have any of those. Otherwise, we're ready to start talking about something new today. Lecture 2, are we excited? Can we pretend we're excited? Yay! Yes, jazz hands. We get that? Exactly. Thank you, Farhan. That was very nice. Jazz hands. Yes. Yellow jazz hands. That's what I'd like to see. I'd like to, makers of Zoom, can we get some yellow jazz hands as one of the options here? All right. Let me move this out of our way and put up the PowerPoints, and away we go. Here we are. Lecture 2. Bivariate association and significance testing. So we have several topics. This should probably take 2 or 3 days to go through. There is also an example that corresponds to this, so that my plan is to talk about the overall concepts in the slides, and then after we talk about each concept, to show you via a separate example document how you would implement these ideas using SAS or Stata. So going along with this lecture on the website, there is another document to be downloaded that's called Example 2. Do you all have that as well? Did you find that? Let me, I'll just put it up real quick just in case. It should be, so there's Lecture 2. That's what I'm looking at right now. There's also Example 2, which is a Word document that has a bunch of syntax and output and annotations for that. And then also there's Example 2 data files. So those are the actual data sets, syntax, and output that generated the Example 2 handout. So when you go to do homework 2, you can start from those Example 2 data files to save yourself some typing. But we're not going to go over the Example 2 data files, but that is how I generated the material that we are going to go over. So we'll go over the handout I created, but the source code for that handout is what I'm pointing to right here under data files. So any questions on that? Good? Okay. All right. Let me know if you do have any. I'm keeping the chat window open. Before everything went to hell in a handbasket last spring, I got a chance to do this split attention thing because in the people who took this class in the spring, some of them were unable to actually show up in person because they were working a job that was an hour or two away and they couldn't make the commute in the middle of the day. So I allowed them to Zoom into the class at the same time that I was teaching a live version. And I have to apologize to those people because I was terrible at reminding myself to like check the chat window to make sure that they didn't have questions, or that I hadn't started sharing my screen, or like some rookie mistake like that. So I'm still prone to rookie mistakes. In the past few days, I attended 2 different Zoom meetings for my department in which I started talking without unmuting myself. I was that guy. I know better and I still did it. So thank you for your patience. And I've noticed that you guys tend to prefer to use the chat window to ask your questions, and I'm totally fine with that. But if you do want to actually talk, that is great too. Just you may have to be forceful at like making sure you jump in there so that I don't overtalk you. Okay? I like questions. Okay. All right, we're ready to go then. So transforming variables, the first topic here. So just to recap a little bit of where we are, univariate summary statistics is what we talked about last time. Ways of describing the content of one variable in isolation at a time. And so you know that variables come in two main categories. So there's categorical variables and there's quantitative variables. There are lots of synonyms for those terms. So to me, a categorical variable is the same thing as a grouping variable or a factor variable, or in SAS language, it's a class variable. The key idea for categorical is that even though you may have numbers entered, they're not numbers, they're categories. And they can be ordinal, which means there's two possible categories. They can be ordered categories, or they can be nominal, which is unordered categories. And in summarizing those kind of variables, all you need to know is the proportion of people in each of the categories. That's it. So that is sufficient. You don't need to worry about reporting things like variance or skewness or any of that, because just knowing how many people are in each of the categories and what the categories are is enough to describe that variable. And a bar chart makes a good visual to present that kind of information more readily. For quantitative variables, numeric variables, basically where the numbers are numbers. I sometimes say continuous variables instead. I'm trying to break that habit, but just know that I will say that from time to time. The idea is that in quantitative variables, the distance between the numbers means something. So it's not just ordered, but it's interval measurement. And in that case, we would want to provide, at a minimum, the minimum value, the maximum value, some measure of central tendency, so usually the mean, but sometimes also the median if the data have some asymmetry to them. We'd want to provide measures of dispersion, so standard deviation, how far off each participant is from the sample mean on average. Alternatively, you can provide the variance. Now, why do I say alternatively? Why wouldn't you need to provide both the standard deviation and the variance? This is the audience participation portion of the program, so go ahead and type on in. SD is easier to interpret, correct, but not where I was going. Do I need to provide both the standard deviation and the variance in a written report, or like in columns of a table or something like that?
No, because they're related to each other. It tells you the same thing.
Yep, they tell me the same thing, and they are related. Homework question: how are they related? SD equals square root of variance. That is it. So yes, the way that it works is you calculate the variance and then you take the square root of that to become the standard deviation. And I make this point because I've actually had a colleague ask me where the variances were. I only see standard deviation. And I'm like, okay, you must have been sick that day. But standard deviation squared is variance, so you need one or the other. If you're describing data, if you're trying to speak to the dispersion of a variable in the metric of the variable, standard deviation is more intuitive. In the next unit, when we start talking about models, and you're trying to differentiate how much information in a variable has been explained or captured by a model versus how much information is unexplained, then we talk about it in terms of variance instead. But just keep in mind that they are two sides of the same coin, so to speak. Good. And interquartile range is something that is sometimes reported too for dispersion. That's not something that shows up in models though. So there's no transition of that idea from just descriptive information to inferential statistics usually. Okay, so now the metric. I've used this term many times. What I mean by that is just your ability to understand, given a number, like what the hell does that mean? Right? Like if Huey comes home from school one day and he says, Mommy, I got a 6 on my test." Now I would have to do some detective work, right? Well, he sounds excited, so I think 6 is good, but I'd have to ask him some more questions. So how 6 out of how many would be the first question. And if it's like, I got a 6 out of 20, then I think to myself, okay, why is he so excited? That's not good. What did everybody else get, right? What did Camden get? What did Abrielle get? Like, what did your cohort get at the preschool? So the metric is something that when you know what the number, when you see the number, you know what to do with it, right? And quantitative variables don't always have metrics that you readily know what to do with. In the social sciences, this is particularly true. So in the physical sciences, you often have metrics that are like so-called real units, like pounds per square inch, or I'm coming up with some distant memory of chemistry of moles and kelvins, and like it's floating back there, but it's like too fuzzy for me to hang on to. But numbers that have some sort of like absolute zero and people know what they mean. Count variables are readily interpretable without you having to do anything to them. How many hurricanes have we had this year? Well, let me think. We're up to what? S in the alphabet or T? Somewhere up there. So I know we've had somewhere like 20-ish. Probably going to end up past 26 once we head over to the Greek alphabet. See, there you go. You can watch the Weather Channel to help you study for this class, and you can start mastering the Greek letter system that the notation uses. So watching TV can be a productive activity for you. More often, the variables that we work with are sum scores of individual items that are aggregated to measure some sort of unobserved construct. By the way, there's a term latent. If you hear that, that means something that's unobserved that you're trying to make some sort of guess about given observed behavior. But you might have an inventory, say, of depression, and a subject gets a score of 31. Well, that's the same problem as Huey's 6, right? It's like, what the hell is 31? Is that a lot? Like, out of how many? Where? Help me with that. Understand 31, or a vocabulary test of 47. So, to get around this problem of sort of squishy measurement, it is often the case that quantitative variables undergo some sort of transformation. So for instance, if I have 6 correct out of 20, I might convert that to a percent correct or a proportion correct. That way I can talk about it on a familiar scale that goes either from 0 to 100% in the case of percentage, or 0 to 1 in the case of proportion. Um, I can take the mean across items rather than the sum, so that then the average for a scale stays within some known boundaries. So for instance, my depression score of 31, if that came from 10 items, each with an ordinal scale of 1 to 5, taking the mean instead of the sum would give me a score of 3.1. Now, what the hell does that mean? Well, I have to look back to the answer choices of what 1 meant, 2 meant, 3 meant, and I know that a score of 3.1 is somewhere near 3, whatever that was on average. So that gives me a little bit better standing to try and understand, to get a sense of what the score means. Sometimes the metric is abandoned altogether in favor of a standardized metric. So there are a lot of measures of development where they are normed so that if you are on a typical age trajectory at a given age, you should have a score of 100, and the standard deviation is normed to be 15, for instance. GRE scores are normed this way. The mean is supposed to be 150-ish, 50-ish, with a standard deviation of 10. So can someone give me an example from your world of scores that have been transformed into something where everybody knows what it means? Cheers. Anyone?
Would the grades being transformed into like a GPA scale be
Yeah,
one?
yeah, that would be one. I thought the highest GPA you could have is 4.0, and then my little brother went and graduated with like a 4.2, because apparently AP classes are on a new scale. But yeah, that's the same idea. A high school that I went to for the first part, freshman and sophomore, they kept it on a scale of 100. So they would take like your average for the class, and that was your GPA and that made it actually a lot more precise. But yeah, that's a great example. Any others you can think of? Okay, so point being, there are ways to make numbers more readily interpretable, and these are very commonly used in the social sciences. The key thing here that unites all of these examples is that these are linear transformations. The information being transformed is done so it's an even transformation. It's not distorted, and so there's no bias introduced, stretching or shrinking of the distances between people. So linear means even. You can think of it that way. One example of a linear transformation that you will get a chance to practice in this class is what is known more generally as centering and often more specifically as mean centering. So when we get to models in which certain variables are viewed as predictors, we haven't talked about this terminology yet, but just a little bit, as reasons why something happened, 0 needs to be an interpretable value on the scale of those variables. But a lot of variables in the social sciences don't have a 0. So they solved the problem by subtracting some constant so that the scale revised has 0 as a meaningful value. So for instance, if I have something like years of education in a sample, what would 0 mean in the context of years of education? Somebody who never went to school. Odds aren't good that I have that kind of person in my sample. So a better approach would be to subtract a midpoint value from the variable so that the new variable has a 0 that's towards the middle. So for instance, I can subtract 12 from education, and the new variable then has a reference point of a 0 as somebody who has a high school degree. And that would become the reference point for my model. I would talk about, here's the predicted score for somebody with 12 years of education, and here's what happens for each additional year of education in terms of their predicted outcome. So this is a linear transformation because all you're doing is subtracting the same constant from each person's score. So if you look at the histograms, they have exactly the same shape. It's just shifted over on the x-axis. So it's purely a transformation for convenience. There's no wrong answer in terms of what constant would be subtracted or added. It just tends to be something that's towards the middle of the data or has some kind of inherent meaning like 12 years of education. Here's another one, and I will apologize in advance for the confusing terminology, but I didn't do it. It's not my fault. Don't shoot the messenger. Another very common linear transformation is z-scoring. And z-scoring puts a quantitative variable onto a standardized metric in which the mean is 0 and the standard deviation is 1. And so therefore, standard deviation squared, variance is also 1. Now, the reason that I have to apologize for this is that z last week, or maybe on Tuesday and last week, was the standard normal distribution, right? It's a different use of z. So the standard normal distribution also has a mean of 0 and a standard deviation of 1. And that's why I think they have the same letter used to describe it. But if you do this z-score linear transformation to your variable, and the way that you would do that, and by you, I mean Stata or SAS, right? This is a thing that you can do with one line of code. It takes each individual score. So y sub I, can you see my giant pink mouse here? Okay, good. Yeah, it's not a coincidence. I have like a 3-foot monitor in front of me and I got really tired of losing my mouse. So I made it giant and pink so that that wouldn't happen. So y sub I, do you remember what that is? Outcome for each person, each individual. Yep, the score. Yep. Minus y bar, what's that? The mean. Yep, the mean of y in this case. Divided by s. What's that one? Yes, the standard deviation in the sample. Good. Yes. So z then gives you in standardized units how far off from the mean each case is. So 0 is the new mean, standard deviation is 1. But doing this z-score linear transformation does not change the distribution of your variable to be normal. It just changes the metric of it so that the mean is 0 and the standard deviation is 1. So to demonstrate this, I have the original income. This is from the general social survey data we played with in example 1, where the average person made about $17,000 a year. So here's the distribution of income. How would you describe this distribution? I'll take gestures, words. Yeah, skewed. Positively or negatively? Which way is this? Positive, yeah, was where the tail's going. And that's because this is a variable that has a boundary, right? You can't make less than no money. You can have less than no money if you're overdrawn, but you can't make less than no money because this is a gross income, right? Net. So if I take this variable that has a mean of 17 and a standard deviation of 13 and some change, and I take each case of this variable and I run it through this formula, the resulting variable looks like this. So it's not normal, right? It's still skewed. It still has a lower boundary. And the reason that it looks a little bit different has to do with how the bins are allocated. The bins are not the same width in the picture on the left to the picture of the right. But the point I wanted to make is that a z-score transformation changes the metric of the variable to have a mean 0, standard deviation of 1. It does not make it normally distributed. It does not give it a standard normal distribution. And that's where it's unfortunate that we use z for both of those ideas.
If the bins were the same between the two examples, would the distribution match?
I'd have to find a way to put the same percent of the cases in the bins because of the differences in the metrics. But yes, then it would. Okay, sorry, I was about to give you another example of something we haven't talked about yet. So I'm going to put a pin in that, come back to it later. But yeah, this is just a rearrangement of the information. It's the same. We haven't changed the relative allocation of income across the people. We've just put it into a metric where we know what 0 means. So the reason we would do linear transformations to give a quantitative variable a more interpretable metric, and also to be able to talk about different variables on the same scale. So when we get to models, so this is all foreshadowing, in other words, we want to be able to talk about whether one factor matters more than another. So after you consider the effect of these variables, do these other characteristics still matter, and what matters the most? In order to be able to say what matters more or the most, they have to be in the same units. Otherwise, it's not a fair comparison. So z-scoring and associated linear transformations like that are one way of putting different variables onto the same scale so that their impacts can be compared. Okay, how are we doing? Hanging in there? All right. Now the other kind.
No, I meant I have a question.
Please.
Okay. Can you go back 2 slides, please?
Yes, I can.
Will you? Okay. Um, there we go. Shouldn't the mean of the transformed variable be 0 here?
In this case, no, because it's not a z transformation. This is an example of just centering, where we subtract a constant, and so the mean is just shifted over by that constant amount.
Okay.
So
Okay.
13.81 minus 12 is 1.81.
You're subtracting the mean from each value, yes?
Yes. So the original variable is called education. We subtract the same constant from each person's score. So if
Oh,
you
okay, so the
picture a
mean gets
column,
shifted by that much.
yeah, and then a second column is created. That is this education that's centered.
Okay.
And the way that I create the column is by taking the first column and then subtracting 12 for each value.
Okay. Thanks.
Sure. Other questions while we're here? Okay. Then the other kind of transformation, nonlinear. And that is where you are changing the metric of a variable unevenly on purpose. So you will see this in two contexts. So I just wanted to sort of plant the seed that this is another type of transformation to watch for. One context is when you're trying to solve the problem that a variable has boundaries and you need it to be unbounded instead. So some transformations are designed to stretch out a variable so that it never really finishes. I'll show you an example of that in like 30 slides from now, maybe. That's necessary to create confidence intervals for certain statistics that have boundaries. The other instance in which you'll see nonlinear transformations is designed to make variables look nicer, to make them more symmetric, or to reduce the appearance and impact of extreme values. And so that's one thing that is unfortunately still taught in intro statistics, that all variables have to be normal because the models that we're going to start from a place of normal. And so there's a lot of transformations that people do to try and like shove your variable into a normal distribution. We don't want to have to do that. That's not necessary anymore. But just so that you know of these things, I just wanted to cover them briefly. So for instance, a logarithm. Now, I'm going to be honest with you, I had to get the definition of logarithm from Wikipedia because that's another thing that's sort of gone along with moles and Kelvin and other stuff, right? It's like, I should know what a logarithm is. It is the exponent to which the base must be raised to produce a number x. Do you know what I think logarithm is? It's a function in SAS. Log variable equals answer. In Excel, it's the function ln. In Stata, it's the function log. So if you don't remember what a logarithm is mathematically, you're in great company. In statistics, it's always the natural log that you will see. It is never log base 10 or base anything else. And so it concerns the number e instead. What happens is that a log transformation is often applied to positively skewed variables, such as income, the picture on the left here, because it takes the lower end, sorry, this way for you guys, and stretches it out, and it takes the upper end that's skewed and just shoves it back in. So this picture on the right is the natural log transformation of the same variable for income. So the right side has been shoved back in, the left side has been stretched out. In advanced statistics classes, when you're trying to predict count values in particular, they will end up predicting the log of the count instead, because that way it's not stopped at 0, because logs can go on into negative number sides. So just know that when you see things like log transformations, square root transformations is another example, that's a nonlinear transformation and you are changing the information. It's not an evenly applied transformation. It's not just for interpretability. It's distorting the information in some way on purpose. Okay, so now that's a lot of foreshadowing because you're going to see these ideas show up in the coming material. In particular, the idea of what linear versus nonlinear transformations will do in looking at associations. We have a little bit of that coming up too, so I just wanted to plant the seed of those ideas. So questions before we switch gears a tiny bit?
Do the nonlinear transformations mainly just dealing with outliers, or are there other reasons why you would do a nonlinear transformation?
Outliers is the primary reason, or skewness more generally, in particularly positive skewed. Response time is a classic example of a variable that tends to have because you can't have a negative response time, right? So it's bounded at 0. But you can be really slow, so it can stretch out pretty far. A log transformation takes a positively skewed variable and makes it look more like a normally distributed variable, which is advantageous when fitting models that assume that the residuals, a word we haven't defined yet, are normal, but normal factors into it. The case in which we will see this applied is in taking a statistic that is bounded, meaning that it can't go past certain points, and trying to find a way to compute confidence intervals for it that obey those boundaries. So a nonlinear transformation will be used to make that happen. Okay, does that help,
Thank you.
Nikki? Okay.
Absolutely.
I have a quick question, just to make sure I understand what's going on. So the natural log, so on the right side, when we see it, that is, so the reason why we're doing that is to reduce the impact of the extreme positives, like you said, to make it look more nicer. Does that make sense?
Some more symmetricer.
Okay.
Yes. So it's it's a whole thing. So here's what happens in intro statistics, and this class is going to be no exception to that rule. The very first things that I'm going to teach you are going to say, we assume that all of these things are normally distributed. And if that's all that you learn, you will be forced to try and take all of your variables and make them to be normally distributed so that you can use the tools that you have. It reminds me of when I went to college and I wanted to install a towel rack in my room, and I opened up the package and it had screws and drill hole, like the plastic things that go around the screws to make sure the towel rack stays up. And I looked at that and I went, well, I've got a hammer, so let's just make this work. And I hammered the screws into the wall. And the towel rack fell down eventually, as one might predict. But it's like that. It's like if all you have is a hammer, then everything has to be a nail. If the only models that you know assume variables are normally distributed, well, you got to make them normally distributed. Um, that is not true. If you only take this class, you might be left with that impression because that's sort of where this class stops. Other classes that I offer follow those models with, well, what if you have a count outcome? What if you have an outcome that's binary? What if you have an outcome that's a percentage? There are models for that. Not everything has to be normal. And there are also models for positively skewed values, and there are models that are designed to reduce the impact of extreme values. So this need to transform things to reduce the impact of extreme scores is an antiquated notion that is dying out, but natural log transformations in particular have a role in creating unbounded versions of things that are bounded that you will come across as useful. So you don't necessarily want to transform variables. It's better to pick a model that matches, but these things are used in statistics, and so I wanted you to have seen them.
Okay, awesome. Thank you.
Sure. Others? Okay. Then changing gears for a bit. So from last time, what we've learned how to do so far in terms of making inferences from a sample to a population, trying to make some sort of conclusion given the limited information that we have. Univariate statistics, trying to describe how a sample mean relates to some sort of hypothetical population mean. It relies on the standard error. As you guys know, standard error is one level of abstraction higher than the data at hand. It describes how far off any given sample mean would be from the population mean. It's an index of inconsistency across samples, and it's defined using the standard deviation and sample size. So you are more expected to be more inconsistent across samples if you have fewer people and if your people are more variable from each other, if there's a larger standard deviation. We can use that magical standard error to form confidence intervals to describe the expected wiggle, and we can use it to perform significance tests, which you're getting to practice in homework 1. If we believe that the population mean is this, right, where this is something that you state a priori, what is the probability of observing the sample mean that we did that was either too low or too high? And if that probability is sufficiently small, where sufficiently small is a cutoff you describe in advance, the cutoff is known as alpha level. Conventional alpha level is 5%. So if the probability of observing the sample mean given the expected null hypothesis is less than 5%, you say that nope, that's unexpected, the result is significant, and we reject the null hypothesis. And the way that we are describing unexpected versus expected in almost every case is this t-distribution, which is a standardized way of expressing how far off what we found in our sample is from what we expected in the population. So this t-distribution has a mean of 0. 0 is where your population expectation would be, and the standard deviation of it depends on how many people you have. So this t-distribution gets flatter and flatter the fewer people that you have. So where the exact cutoff is for what t value would correspond to significant, would correspond to a probability of less than 5%, shifts as a function of the number of people in your sample. And so the software does a much better job than we can of taking all of this information and simultaneously giving you the most accurate results in terms of the t-value given that degree of freedom, given your alpha, and given whether it's one side or two sides. Okay. From univariate to bivariate is where we're heading then. So bivariate means 2. Ta-da! So looking at 2 variables at a time, and more specifically trying to gauge how associated they are. And the way that we will gauge how associated they are depends on what kind of variable. So there are different techniques for describing associations between quantitative variables, between categorical variables, and for some combination of the two. And this is very much a if this, then that kind of logic. For each of these types of associations that we're going to talk about, we will need some kind of index of the association, and which index that is varies. But we'll get an estimate of it, meaning according to our sample, what is the result that we found? And just like we did for the sample mean versus the population mean, we will compare our sample's estimate to some sort of expectation. In looking at bivariate associations, it is almost always the case that the expectation is no association. Doesn't have to be, but that is by far the most common approach. And so 0 is our new population benchmark. And I keep making the line in the sand or the stick in the sand or whatever you want to call this gesture right here that you're paying extra tuition dollars for. Right? That's my benchmark. And so I'm setting this a priori, like what is the comparison against, and now what did I get? That's always the question. So we're talking about null hypothesis significance testing of an association between 2 variables relative to an expectation of no association whatsoever, or significance hypothesis inference testing, or SHIT, according to Jacob Cohen, as it were. So the first instance of this I'm going to give you is our new friend Pearson correlation. Pearson is a guy. He made up a lot of things. So there's a lot of stuff named after him because back in the day when you were an old white man, you named shit after yourself. And less so today, but there's still quite a bit of that. So we'll get to know lots of famous old white dead people. Pearson correlation. How many of you have heard of this before? Okay, half and half. So the good news of Pearson's correlation is that this is readily available in many programs, including Excel. In SAS, you'll learn how to do this using proc_core, where core stands for correlation. Proc stands for procedure, by the way. And in Stata, the command is pwcore, where pw stands for pairwise. So we'll see examples of how to get this information. It's very quick and easy to do. So Pearson correlation, our new friend. Okay, there we go. So let's say that we have 2 variables, and I'm going to call one of them X and I'm going to call one of them Y, just because I need 2 different names. Come back. There we go. Pearson's correlation is often described graphically using a type of plot that's known as a scatter plot. So if you just took like 2 columns of data and just like threw it at the wall, like that's what you get here. But more specifically, one variable, the values are shown on the x-axis, and the other variable's values are shown on the y-axis. And the association between them then is conveyed by the pattern of the dots, or the scatter, as it were. So in Pearson's correlation, more vocabulary, so more working memory exercises for us to engage in. We will call a correlation R. I don't know why it's not C, but it's R, just because. This is ubiquitous across the world. Correlations are R. Like that is just the rule that everyone has decided on. Just like we had a sample version and a population version of the mean and the standard deviation and such, the sample version is R and the population version is supposed to be a Greek letter that looks like P, but that's rho. It looks like P to me, but this thing right here, this is known as rho. Rho will also be used for another kind of correlation in like a half hour from now or whenever we come back next, but for now, this is population correlation. So you will see rho referred to on your statistical output. They actually spell it out as rho rather than trying to make the symbol. But Pearson's correlation, when you're describing what it is in a sample, R is what you call it. This is an example of a bounded statistic. So this is the first time we've seen this. A population mean can be anything, right? Sample mean can be anything. Standard deviation, I guess it's not the first time, is bounded at 0, but it could be any positive number. Well, R is bounded above and below. It ranges from -1 to 0, which means no association, to 1. So the strongest relationship is either -1 or 1, and the sign tells you which way the relationship goes. So if we go through the pictures here, if as x goes up this way and then y goes up, that is a positive association. And if that association is perfectly in sync, that would yield a Pearson's correlation of +1. So it looks like this. That never happens in real data. You will never see that in your life unless you make up the data. More likely, you will see something that looks like this with varying degrees of messiness to it. So these two pictures in the middle here depict an increasingly less powerful correlation, a lower magnitude correlation. Lower in terms of the number line, but lower also in terms of the strength, where it looks a little more random. This is more likely what you're going to see in real data. The picture in the middle, R equals 0, is no correlation. So that means if I know what your score is on X, I have no freaking idea what your score is on Y. That's a 0 correlation. They are unrelated to each other. A positive correlation is like as X goes up, Y goes up to at least some extent. The other pictures on the right show relationships that are just as strong, but in the opposite direction. So as Y goes up, as X goes up, Y goes down is a negative relationship. And those can range from 0 down to -1. So the sign of the correlation tells you which way the association goes. Positive means as X goes up, Y goes up, or as X goes down, Y goes down. A negative relationship is as X goes up, Y goes down, or as X goes down, Y goes up. You can talk about it whichever way you want. The magnitude of the correlation is given by the absolute value of the number. So if I have a correlation of 0.8, that is actually a stronger degree of relationship than a correlation of minus 0.6. And I would say the same thing in reverse. If I have a correlation of minus 0.6, that's stronger than a correlation of 0.3. Does that make sense? So the sign is not like on the number line. It's just telling you which way the association goes. The strength of it is how close it is to 1. Okay, come on. You can do it. No. I have animation and I know what it should be doing. Come on. It's thinking about it. Yeah, see, it's angry with me. Only thing worse than a giant pink arrow is a giant pink hourglass. But now we're back. All right. So how do we get this thing? So again, my promise, you don't need to memorize these formulas, but I want to show you where this stuff comes from. First thing we need to do is figure out what the mean and the variance is for each of the two variables. So introducing some notation that is variable specific. The formula for mean hasn't changed. It's the sum of all of the observations on a variable divided by the sample size. But note that I'm denoting the mean for x versus the mean for y. So x sub I has a mean for the sample of x bar, y sub I has a mean of y bar. And likewise, their variances, the one for x is each individual value on x minus the mean for x, square it, sum it up, divide by n minus 1 because we had to know the mean for x in order to do this. That's why the 1 penalty function shows up. This is denominator degrees of freedom. And so I have different means and consequently different variances for each of the x and y variables. So that part we already know how to do, just to change in the way that we talk about the notation. Now to put them together, the next step is to compute something that's called covariance. This is not something that you will come across immediately. It is something that will show up again like 2 or 3 classes from now. Covariance is a big deal later on. But for now, it is an intermediate point to get to the correlation. So covariance concerns the extent to which cases that are above the mean on x are also above the mean on y, or above the mean on x, below the mean on y, but it retains the scale of the individual variables in the first place. So more formally, covariance is computed as how far off the mean you are on x times how far off the mean you are on y. So if you are above both, it'll be a positive value. If you are below both, that's 2 negatives multiplied together, that's also a positive value. And so if we sum those up and divide by n minus 1, we end up with a number that describes the association between these variables, but it's a number we don't know what to do with because it depends on what a unit is in x and what a unit is in y. We can look at the number's sign and discern what kind of association it is. So a positive covariance would result from cases that are more likely to both be above the mean on x and y or more likely to both be below the mean. And an opposite tendency would be a negative covariance. But we don't know what to do with this. So we start with covariance and we want to change it into something that's more useful. So to make this a little more concrete, let's say that we have a small sample, 10 men, and we've measured their height and weight. So x is going to be their height in inches. Let's say that this sample of fake people has a mean of 72 inches and some change. Their standard deviation is 6.5, and in pounds, the average is 235-ish with a standard deviation of 20. Well, if I feed these two columns for x and y into these formulae, I end up with a covariance of 135. So it's like, what the hell is that? It's 135 inch-pounds. Hello, cat. This is like, you know, I used to have a cat that would like to do that too. They always want to be like on your lap, like whatever you're doing. It's a very nice comfort. But yeah, 135 inch-pounds. I don't know if that's a lot. I know that it's positive, so I know that taller people tend to be heavier, but I don't know what that means. So the solution to this is a linear transformation, trying to strip off the differences between these variables in their units, put them into some sort of standardized metric, and then we can talk about the covariance between the standardized versions of the variables. And that covariance of the standardized variables is our friend correlation, Pearson correlation in particular. Yes, Sebastian is the cat. Hello, Sebastian. You get a shout out from the instructor. So if I have the covariance between these two variables, 135 inch-pounds, and I divide by the standard deviations of these variables. So the means have already been taken care of because the covariance is expressed relative to the means. So any differences in means, that's already handled in computing covariance. But I still got to take the spread of the variables into account and standardize that part. So by dividing by the standard deviation of each of these variables, I end up with a metric that goes from -1 to 1. So this set of 10 observations gives me a correlation of 0.99. So there's almost a perfect correlation between height and weight in these 10 example cases. So now I know what to do with that. I know that that's about the strongest relationship that I can have, that if you are taller than somebody else in my sample, you are almost perfectly likely to be heavier than somebody else. Okay. So one thing that is potentially problematic with this formula is that it doesn't account for sample size. Everything else that we've done so far has had an n in the formula somewhere, and Pearson's correlation does not. So why would this potentially be a problem? Well, think about if we only had 2 people. If we had 2 people, a scatter plot with 2 points in it here, and I wanted to compute a correlation between them, what would my correlation be? Perfect, because 2 points make a line. Well, obviously it's not a perfect correlation. We just don't have enough information to be able to gauge what it is. So the more people that we have, the less likely the points are going to make a line and the better the estimate. So for that reason, at some point, reviewer 3 may ask you to report something that's known as an adjusted correlation. Now, this has never happened to me, but just in case this happens to you, I want you to be able to make reviewer 3 happy so that you can get your paper published. The adjusted R starts with the original Pearson's R and changes it as a function of sample size. So in our case with 10 cases, this is something that we might want to consider looking at, and it works out to be 0.993 instead of 0.994. So I wouldn't change anything about my conclusion as a function of that, but you can envision a situation in which if you have a very small sample and a relatively weak R, that you might want to be more cautious as to what that R could be to reflect the lack of information that's going into it. So an adjusted R would be potentially a more conservative approach in that case. Why wouldn't we just use adjusted R? Wouldn't it be more accurate? Yes, but that's not what people do. You're absolutely right. It probably is more accurate. And also there's an inconsistency that I stumbled across in making these slides that makes no sense. The degrees of freedom for computing covariance, you use n-1, so this formula right here, but when we test this correlation, it suddenly becomes n-2. To me, that seems wrong, but that is like ubiquitously what everyone does. So yeah, I think adjusted R is a perfectly reasonable thing to do. You just want to make sure that you call it that. A sample size adjusted Pearson correlation would be what I would call it that. And certainly in the context of models, when we talk about R there is probably a more likely push towards doing adjusted statistics in that case too. Okay. Other questions? Okay. So this R thing, it's a number that we know what to do with immediately. If it's 0, these two things are unrelated. If it's positive, they are related to at least some extent, where as x goes up, y goes up, as x goes down, y goes down. If they're negatively related, as one goes up, the other goes down. Like, we know that much. So R is actually something that we'll call more generally an effect size. It's a number that conveys the strength of an association in an absolute sense. It's a metric that we know what to do with because it's been standardized to remove the influence of different means and variances across variables. Hang on, we got one more. There we go. But for significance testing, so when we did significance testing for the means, right, the magical connection to get to your p-value was to have a standard error. That is not the case in testing a correlation for significance. So let me give you the logic of this process in the context of testing a Pearson correlation. So what I'm describing is known as null hypothesis significance testing. You've seen one instance of this in comparing a sample mean to a population mean. Now we're going to see another in comparing a sample correlation to an expected population correlation. So the null hypothesis. Null in this context does mean 0, but it doesn't have to. So in the slides for lecture 1, we had a population mean that was 10, and we wanted to compare a sample mean that was a little bit above 10. In the context of testing a Pearson correlation, the null hypothesis is almost always that rho, that p-looking thing here, is 0. So testing against no association whatsoever as your benchmark. That is by far the most common approach, but it doesn't have to be. The software will let you specify an alternative null hypothesis. If you have some reason to believe that your correlation is supposed to be 0.5, and you want to see how your sample's correlation compares to that expected 0.5, you can totally do that. That's okay. It's just a lot less common because that requires you to have some sort of basis for generating the 0.5 prediction. So 0 is a much easier prediction to make because it requires no information whatsoever. It's the neutralist benchmark that you can come up with. The lazy person's null hypothesis, as it were. So the alternative hypothesis then is if you believe that your correlation could be either positive or negative. So remember, this is something you're supposed to set up in advance before you look at the data. Then you would want a two-tailed test, the idea that your correlation is not 0. So it could be high, could be low, don't know. That's the alternative test. There we go. So more generally, in this process of doing a significance test of a sample result relative to some population expected null hypothesis, you have to decide a priori if you want one side or two, meaning are you willing to accept a result as unexpected if it's either too high or too low, or in this context, if the correlation is either positive or negative, that is almost always the appropriate course of action. And what level of confidence you want to have. Where do you want unexpected or significant to start? That's known as alpha level. So if you have an alpha of 0.05 as your most typical case, then you're saying 95% of the time defines expected fluctuation around my population anticipated null hypothesis. And if the result would occur less than 5% of the time, given the null, then that would be flagged as significant, reject the null, unexpected, all of that stuff. The third thing that you have to know, but in reality this is decided for you, is which sampling distribution you're referring to decide how to gauge what 95% is and what 5% is. And there's really only 4 that you're going to come across. The first one that we met was Z, the standard normal distribution. And that is used if you're testing one idea. So in the context of bivariate association, if you're testing one association between two variables or one mean, for instance, and you're ignoring the amount of people that you have going into the test. So that's Z. That's almost never appropriate. We're going to use T the vast majority of the time. And that's the T that we met, the Guinness Brewery T, that guy. The flat normal. T is going to be our friend. T is used to test one thing and to do so while paying attention to the number of people that are contributing to that estimate. So you have to have how do I say this? A more noteworthy result the smaller your sample is. The smaller your sample is, the harder it is to cross that threshold into unexpected. And T acknowledges that, whereas Z ignores it. So almost everything you're going to see in this class is going to be T. Later on in this lecture, we will meet Z's cousin. This X-looking thing, this is chi-square. Z squared is chi-square. Chi-square is used more generally to test more than one idea simultaneously. So when an association requires knowing two things at once, I'm trying to avoid using the term numerator degrees of freedom, but for those of you who've seen this before, that's what I'm talking about. And likewise, if you take T and square it, that's our friend F. So the F distribution is used to test more than one thing simultaneously while paying attention to the sample size in doing so. So these are the four things that you will see. And in reality, when you ask your software to do a given type of association, it will spit out the right one. So this isn't something that you need to have memorized per se. It's more just anticipating what you're going to get. It's usually going to be T or F in the things that we'll look at. Okay, questions? Did I see a hand? Okay. So given this demarcation of where unexpected versus expected lies, then we get into the horrible logic of the null hypothesis, reject and do not reject. So if the test statistic is headed into unexpected territory, if it crosses that threshold decided ahead of time, in practice that means the p-value that shows up on your output is less than the alpha you decided on. So if you decide on an alpha of 5%, what you're saying is that less than 5% of the time, if the null hypothesis is true, we would see a result that extremely different. If you are in that situation, we are rejecting the null hypothesis. That's just saying that it's unlikely that this sample would have been found from a population characterized by the null. It is unlikely that we'd get a correlation of 0.9 if the true association were 0. So it's always relative to that benchmark that we set up in the first place. What is your expectation? Relative to that, how frequently would you have found what you got in your sample? If it's in that unexpected territory, p less than 0.05, it's significant. The opposite, if it's within expected, if it's not that different, not enough different than what you expect from the null hypothesis, the middle, then we do not reject or retain, or the way that people talk about it is just, it's not significant. Okay, can you say insignificant? Here's a quiz for you. No, someone will yell. They will yell loudly. Insignificant is wrong. It's a value judgment. Like your research can be insignificant, but your result could not be. Not that any of your research is insignificant. I'm just trying to be funny. So yes, you can say not significant or non-significant if you want to use it as like an adverb. I tend not to hyphenate, but I've seen it either way. So in practice, you would say, the correlation is not significant, meaning I don't have enough evidence to say that it's unexpected. Like it's within the realm of possibility if that it's within 0. The reason that you can't say accept the null hypothesis is that if you have a large enough sample, you will never not reject it. Like the null hypothesis, in some views, is sort of a stupid benchmark because it's never really true. So it's just a question of how much evidence that we have to say that it's unlikely, and that depends on your sample size. So to that point, here is how we get a t-test statistic given a Pearson correlation R and our sample size n. So t is a function of R times the square root of our sample size minus 2 over 1 minus that same R squared. And because t is a test statistic that wants to know how many people are contributing to this test, it's the denominator degrees of freedom that go with the t is n minus 2. So that's telling you how flat the reference distribution is, where the fewer people, the flatter it is, and the more extreme result you have to have before it hits that 5% territory. So in this example, if I put in the unadjusted correlation of 0.994 into my t formula, I get a t of 25. And the p-value that goes with that, I have to use scientific notation to convey. So if you see this pop out on your output, by the way, 5 point something with an E, just as a reminder, that's how many decimal places you have to move over before you start hitting a number, where you're moving to the right of the decimal if E is negative and to the left if it's positive. So this result would be reported as less than 0.0001 on the output. So it's not really 0, but it's 0 to 4 decimal places. So yeah, it's really, really, really unlikely that we would find a correlation of 0.994 if the true population were zero, the correlation were zero. So it looks like it came from another distribution altogether, is sort of the conclusion that one might draw. The same story holds if we substitute in the adjusted R that controls for sample size. It's a t of 24 instead of 25. Do you remember what the loose cutoff is for when t is significant? What's your eyeball number? I said this a couple times last time. 0.10 would be a p-value. 2, yeah, 2-ish. So how 2-ish, t of 2-ish is generally your cutoff. What ends up happening in software is that they don't give you the t that goes with the correlation. They only give you the p-value. So you will get the correlation estimate, like the 0.99 here, the sample size, and you will get the p-value. It does all of that under the hood for you to figure out what t should be and what the right reference t should be given your sample size. But yeah, t of 2-ish is generally where a significant cutoff is. Okay. How are we doing? Good. So welcome to Pearson correlation. It tells you how associated two quantitative variables are. It ain't perfect, but it's a starting point. So next time we'll get to talk about the ways that it can be improved upon, because Pearson's correlation is not the only game in town. All right. Any other questions before we adjourn? All right, then let me know if you need anything. Office hours at 3:15. Otherwise, stay safe, stay sane. Have a good weekend.
Thank you.
Thank you.
Thanks, Lisa.
See you next